Bismillahirrahmanirrahim. Hello students, welcome to the electrical engineering channel. In this lecture, I am going to demonstrate the electric field due to a continuous volume charge. So in the previous lecture, we discussed the electric field due to a point charge, but there can be cases in which we have charge distributed over a volume. So in if we have a charge which is distributed over a volume, we have to first find out the total charge, and in such scenarios we will be given the volume charge density. So whenever a charge is distributed over a volume, then the volume charge density will be given, which will be used to first calculate the total charge, and after calculating the total charge we can use the same expression to calculate the electric field intensity. So how I, how we can calculate the total charge due to a volume charge distribution? We have to first divide the entire volume into infinitesimal segments or infinitesimal elements, and the width or the volume of the single element or a single piece will be called as differential volume, and that will be represented by delta V, and the total charge enclosed in that differential volume element will be delta Q. So the volume charge density in that case will be equal to the total charge in this volume divided by the total differential volume, so it will be charge per unit volume. So if we apply the limit, or if we assume that the volume of this differential element is very small, then we can apply this limit as delta V tends to 0, delta Q divided by delta V, and by the definition of the derivative, this will be equal to dq divided by dV. Suppose delta Q charge is enclosed in incremental volume delta V, then volume charge density is defined by rho V equal to dq divided by dV. And from this expression, total charge dq will be the product of volume charge density and the differential volume. So the total charge can be calculated by taking the volume integral of this expression, and volume integral will be basically the triple integral. So differential electric field due to this differential charge dq will be equal to dq divided by 4 pi epsilon r minus r dash vector divided by r minus r dash magnitude cube, and the total electric field due to the total charge will be given by the volume integral of this expression, so it will be equal to the triple integral of this expression. So that is very simple. If we have this expression for the volume charge density, we can first calculate the total charge, and then we can calculate the electric field intensity. So we will solve a couple of examples to have a deeper insight into the electric field intensity due to a volume charge distribution. And in the first example, we are given the volume charge density as an expression 1 over x cube by cube z cube, and the limits of x, y, and z are given as x, y, and z magnitudes are varying from 0.1 to 0.2. So these are actually two expressions, or we can say that these are actually two inequalities, because we are given the limits of x mod, y mod, and z mod. So first x, y, and z will be considered as positive, and then x, y, and z will be considered as negative. So these are actually two inequalities. So if we consider the first variable of integration x, then this inequality will be written as this, and this will become, the first inequality will become 0.1 less than or equal to x less than or equal to 0.2, and in the second inequality this x mod will be written as minus x, so it will be 0.1 less than or equal to minus x less than or equal to 0.2. Now we have to multiply this inequality with negative sign, so it will become minus 0.1 minus 0.2, this will become x, and these signs of inequalities will become opposite, so it will become greater than or equal to, and this will also become greater than or equal to. Now we have to reverse the two limits to get the same convention as we are using over here. So first we will have less than or equal to, then we will have less than or equal to. So in order to use the same inequality sign, we have to bring this minus 0.2 to the left side and minus 0.1 to the right side. So this is the second inequality, and now we will have to calculate the total charge which is located in this region. So in the first region, this volume integral will be evaluated, and in this volume integral, this inequality will be used for all the three variables of integration. So x, y, and z will be varying from 0.1 to 0.2. And in the second expression, we will use the same expression, but this inequality will be used for the variables of integration, and it will be minus 0.2 to minus 0.1 for x, y, and z. Now, it is very simple to evaluate the integral, the triple integral of these two expressions, and all the steps are written over here. So the integral of 1 over x cube is minus 1 over 2x square multiplied by this and this. These are the limits of integration, and similarly, these are the three expressions for the second integral, and these are the limits. So after substituting these limits, we will get 37.5 minus 30.75, and the net charge will be equal to 0, because 37.5 is the total charge enclosed in this region, and minus 37.5 charge is enclosed in this region. So the total charge will be, the net charge will be equal to 0, because this is positive charge and this is negative charge. And in the second example, we have to calculate the total charge in the first part, and we are given the volume charge density as 0.2 microcoulombs per meter cube, and this is the region which is given over here, and in this region the volume charge is present. So r is equal to 3 to r is equal to 5. So r is a spherical variable, so we will have two spherical surfaces. One surface is r is equal to 3 centimeter, second surface is r is equal to 5 centimeter, and in between these two surfaces we will have the volume charge. So the total charge q will be equal to rho v dv, and we can easily evaluate the volume integral of this expression. So in spherical components, dv is equal to r square sine theta dr d theta d phi, and rho v is equal to 0.2 micro. And the limits of integration are also given from 3 centimeters to 5 centimeters, so it will become 0.00 to 0.05. So after evaluating this triple integral, we will get the final answer of 82.1 picocoulomb. And in the second part, we are given that if half of the total charge is enclosed in the region from 3 centimeter to r1, then calculate the value of r1. So we will assume that q1 charge is located in this region from r is equal to 3 centimeter to this r1. So q1 will be equal to q divided by 2, so it will be 41.05 picocoulomb. And we have to again evaluate the volume integral of the volume charge density to calculate the charge q1, and q1 is given, so we can easily calculate r1. So these will be the limits of integration, and after evaluating this integral, we will get 0.2 into 10 to minus 6 divided by 3 into 4 pi into this. So after rearranging this equation, we will get this expression, and r1 will be equal to this expression, and its power is 1 by 3. So when we evaluate this expression further, we will get r1 equal to 4.24 centimeters. So clearly 4.24 centimeter is lying between 3 and 5, so it means our answer is correct. So that is all about our today's lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.